All right, welcome back. In this lecture, we begin looking at examples of characteristic roots and characteristic vectors of a square matrix, and using them to calculate functions and determine properties of the matrix. Now, in this lecture video, we're going to be looking at what we'll call example 1.1. Let's take a look. So let's let cap sigma be the 2 by 2 matrix given here. So the 1, 1 entry is equal to 4. The 1, 2 entry is equal to 1. The 2, 1 entry is equal to 1. And the 2, 2 entry is equal to 4. Now we're going to do several things in this example. The first of which is to find lambda 1 and lambda 2, the characteristic roots of cap sigma. We'll then find the general form of the characteristic vectors of cap sigma corresponding to each of the characteristic roots lambda 1 and lambda 2. We'll then verify that C1 prime times C2 is equal to 0, where C1 and C2 are arbitrary characteristic vectors of cap sigma corresponding to lambda 1 and lambda 2 respectively. So C1 is an arbitrary characteristic vector of cap sigma corresponding to lambda 1, and C2 is an arbitrary characteristic vector of cap sigma corresponding to lambda 2. Now we'll then use those arbitrary characteristic vectors to find length 1 characteristic vectors of cap sigma, which we will denote by A1 and A2. So A1 will be a length 1 characteristic vector of cap sigma corresponding to lambda 1, and A2 will be a length 1 characteristic vector of cap sigma corresponding to lambda 2. Now, once we've done all that, we're going to verify some of the results that we saw in a previous lecture video. In particular, we're going to verify that the trace of cap sigma is in fact equal to the sum of the characteristic roots, so lambda 1 plus lambda 2. We'll then verify that the determinant of cap sigma is equal to the product of the characteristic roots, so lambda 1 times lambda 2. We'll then answer the following questions. Is cap sigma positive definite? Is cap sigma positive semi-definite? And is cap sigma non-negative? We'll then follow that up and answer the question, is cap sigma a valid covariance matrix? And then we'll extend it further and answer the question, could cap sigma be the covariance matrix of a multivariate normal distribution? If so, then we will define a two-dimensional random vector to have a multivariate, in particular a bivariate normal distribution with a mean vector that we'll denote by mu and a covariance matrix that we'll denote by sigma, which is the matrix we're working with. And then we'll find and answer the following. So we will find the variance of x1, we'll find the variance of x2, and we'll find the correlation of x1 and x2. And then finally, we'll answer the question, does a PDF exist for this distribution? All right, so let's take a look at the solution. So first we're going to find the characteristic roots of cap sigma. So what we have to do first is to find the characteristic equation for cap sigma. And you'll recall that this is given by setting the determinant of the difference between cap sigma and the matrix lambda times the identity function, setting that determinant equal to 0. Now, the difference between cap sigma and the matrix lambda times the identity function is the 2 by 2 matrix shown there in brackets, in the matrix brackets. So the 1, 1 entry in that difference is 4 minus lambda. The 1, 2 entry is 1. The 2, 1 entry is 1. And then the 2, 2 entry is 4 minus lambda. And we have to take the determinant of that 2 by 2 matrix. Now you'll recall that the determinant of a 2 by 2 matrix is equal to the product of the diagonal elements minus the product of the off-diagonal elements. And so it's going to be equal to 4 minus lambda times the quantity 4 minus lambda. And then from that we subtract 1 times 1. And so when we multiply that out, expand it out, we get the characteristic polynomial of cap sigma, which is lambda squared minus 8 lambda plus 15. And so we set that equal to 0, and that gives us the characteristic equation of cap sigma. Now, to find the characteristic roots of cap sigma, we solve that equation for lambda. Now, obviously, because it's a polynomial of degree 2, there are going to be two solutions, two roots of the polynomial, two solutions of the equation. And we can get at those by factoring the characteristic polynomial. So we factor lambda squared minus 8 lambda plus 15. All right, so if you can remember back to algebra, okay, and do that factorization, we see that that factors as the product of lambda minus 5 and lambda minus 3. Now, that product, the product of binomials, is equal to 0 if and only if lambda is equal to 5 or lambda is equal to 3. And so the solutions of the characteristic equation of cap sigma are 3 and 5. And so the characteristic roots of cap sigma are therefore lambda 1 equal to 5 and lambda 2 equal to 3. Now you'll remember that the way we assign these characteristic roots to the lambda notation, lambda 1 is the largest characteristic root, lambda 2 is the next largest, and so forth. And because we've only got two roots here, lambda 2 is going to be the smallest. All right, now let's find characteristic vectors of cap sigma. And so let's let lambda be an arbitrary characteristic root of cap sigma. Then by definition, we have the following equality. So cap sigma times c, the vector c, which is an arbitrary characteristic vector corresponding to lambda, that is equal to lambda, the characteristic root, times c, the characteristic vector of cap sigma corresponding to lambda. Okay, so we can see here that internally the entries in the 2 by 1 c vector are labeled c1 and c2. All right, and so if we plug in the matrix for cap sigma, so 4, 1, 1, 4, and then times the c vector, so c1 and then c2, and then that is equal to lambda times c, and so in terms of the entries in the resulting vector, they would be lambda times c1 in the 1, 1 entry, and lambda times c2 in the 2, 1 entry. Okay, so and the other thing is that we're assuming that this is a non-zero vector c. Okay, and so we have this vector equation, and in order for that equality to hold, the corresponding entries must hold. And so that implies that 4 times c1 plus c2 is equal to lambda times c1, and also c1 plus 4 times c2 must be equal to lambda times c2. And so we have two equations with two unknowns. And so now we have to use some algebra to try to solve this equation. So we're going to subtract 4 times the second equation from the first equation and then solve that for C1. And if we do that, we get C1 in terms of C2 as well as lambda. And so the expression we have, the equality we have, is C1 is equal to the quantity 4 lambda minus 15 all over lambda times C2. So this results in one equation with two unknowns. And so what that implies then is that the characteristic equation has an infinite number of solutions, right? There's not a unique solution. There are an infinite number of solutions. And so what this implies then is that there are infinitely many characteristic vectors of the matrix cap sigma corresponding to this arbitrary characteristic root of lambda. Now let's let C2 be equal to t, where t is an arbitrary non-zero real number. It follows then that any vector c of the following form, where c is equal to the 2 by 1 vector shown here, 4 times lambda minus 15 all over lambda in the 1, 1 position, and then in the 2, 1 position we have 1, and then that 2 by 1 vector is multiplied by this arbitrary non-zero real number t. So any vector c that has that form is a characteristic vector of cap sigma corresponding to the characteristic root lambda. So this is a general formula that we can use to find a characteristic vector of cap sigma corresponding to whichever of the characteristic roots we're talking about. So this, you can see here that this formula involves lambda as well as t. All right, and so we can use this formula to find characteristic vectors of cap sigma corresponding to each of lambda 1 and lambda 2. So let's do this for lambda 1. So using the formula on the previous slide, we see that any vector of the form c1 equal to, and then we have the 2 by 1 vector where we are replacing lambda with lambda 1 equal to 5. So 4 times 5 minus 15 all over 5. So that's 20 minus 15, which is 5 over 5, so that's 1. And then, so we have the 2 by 1 vector, 1, 1, and then we're multiplying that by the scalar t. All right, and so we end up with a 2 by 1 vector with entries t and t. So any vector of that form is a characteristic vector of cap sigma corresponding to the characteristic root lambda 1 equal to 5. Now that's an arbitrary or general characteristic root or characteristic vector of cap sig corresponding to lambda 1 equal to 5. We're going to be particularly interested in a characteristic vector of length 1. To be of length 1, it's necessary that the length of the characteristic vector be 1, and if the length is 1, then the squared length is 1 as well. Now, the squared length of C1 is equal to C1 prime times C1. And so to be of length 1, it's necessary that 1 equal to C1 prime times C1. And when you carry out that inner product, that's equal to 2 times t squared. Now again, t is a scale factor for the characteristic vector, and we can set it to any non-zero value that we want. And if we want the vector to be of length 1, then as we see here, the value of t needs to be either a plus or minus 1 over the square root of 2. If we do that, then the resulting vector will be of length 1. So doing that, we see that length 1 characteristic vectors of cap sigma corresponding to the characteristic root lambda 1 equal to 5 are given by the following. A1 equal to the 2 by 1 vector with entries 1 over the square root of 2 and 1 over the square root of 2, and also the negative of that vector, which is the vector in the opposite direction, with entries negative 1 over the square root of 2 and negative 1 over the square root of 2. And so that is, each of those is a length 1 characteristic vector of cap sigma corresponding to the characteristic root lambda 1 equal to 5. All right, next, let's look at characteristic vectors of cap sigma corresponding to lambda 2 equal to 3. So substituting 3 in for lambda into the general form for the characteristic vectors gives vector C2, the 2 by 1 vector, the 1, 1 entry being 4 times 3 minus 15 over 3. So that's 12 minus 15. That's negative 3 divided by 3. That's a negative 1. And so we have the 2 by 1 vector equal to negative 1 and then 1 and then times the scalar t. And if we multiply both of those entries in the 2 by 1 vector by t, then we get the 2 by 1 vector negative t and positive t. So any vector of this form is a characteristic vector of cap sigma corresponding to the characteristic root lambda 2 equal to 3. Now we want a length 1 characteristic vector of cap sigma corresponding to lambda 2 equal to 3. And so again, to be of length 1, it's necessary that C2 prime C2, which is the inner product of C2, and that's equal to the squared length of C2. It's necessary that that squared length be equal to 1. And so when we carry out that inner product calculation, we see that that is again equal to 2 times t squared. And so that implies that t can be either a positive 1 over the square root of 2 or negative 1 over the square root of 2. And so when we plug those values in, we get two different length 1 characteristic vectors. The first one, A2, being equal to negative 1 over the square root of 2, and then positive 1 over the square root of 2. And the negative of that vector, which again is the vector in the opposite direction, the 2, 1 vector containing the entries positive 1 over the square root of 2 and negative 1 over the square root of 2. So to summarize the results thus far, we have our 2 by 2 matrix, the characteristic roots of which are lambda 1 equal to 5 and lambda 2 equal to 3. The length 1 characteristic vector of cap sigma corresponding to lambda 1 equal to 5. We have two such length 1 characteristic vectors as shown here. And then the length 1 characteristic vectors of cap sigma corresponding to lambda 2 equal to 3 are given at the bottom of the slide. Now next, we want to verify that C1 prime times C2 is equal to 0. Now the reason we want to look at this, we want to verify this, is that you'll recall from a previous lecture video, we said that characteristic vectors of a matrix corresponding to different characteristic roots are orthogonal. And they are orthogonal if and only if their inner product is equal to 0. And so we want to verify that C1 and C2, because they are characteristic vectors of cap sigma corresponding to different characteristic roots, that they are in fact orthogonal. And we show that by showing that their inner product is 0. So again, C1 is equal to the 2 by 1 vector containing the entries t and t, and C2 is the 2 by 1 vector containing the entries negative t and positive t. And so when we calculate the product C1 prime times C2, we see that we get negative t squared plus positive t squared, and that is obviously 0. So because of that, this implies that the two vectors C1 and C2 are orthogonal, as the theory said it should be. All right, next, we want to verify what we had said in the previous lecture video, that the trace of a square symmetric matrix can be calculated as the sum of the characteristic roots. Now, we know that the definition of the trace is that it's the sum of the diagonal elements in the matrix, but it's also equal to the sum of the characteristic roots. And so we want to verify that for this particular situation. And so the trace of cap sigma, using the definition, as the sum of the diagonal elements is 4 plus 4, which is 8. The sum of the characteristic roots is 5 plus 3, which is also 8. And so we see that that result does in fact hold for this particular situation. Next, we want to verify that the determinant of cap sigma is equal to the product of the characteristic roots. Now you'll recall that the determinant of a 2 by 2 matrix is equal to the product of the diagonal elements minus the product of the off-diagonal elements. And so that would be, in this case, 4 times 4 minus 1 times 1. 16 minus 1, which is 15. The product of the characteristic roots is 5 times 3, which is also 15. And so again, we see that this property holds for this example as well. All right, so now we want to determine whether or not the matrix is positive definite, whether it's positive semi-definite, and whether it's non-negative. So the first question, is cap sigma positive definite? And the answer is yes. Since both characteristic roots of cap sigma are positive, cap sigma is positive definite. Is cap sigma positive semi-definite? The answer is no. Although both characteristics of cap sigma are non-negative, neither of them is 0. Therefore, cap sigma is not positive semi-definite. And then finally, is cap sigma non-negative? Yes, it is. Since cap sigma is positive definite, it is non-negative, because a matrix is non-negative if and only if it's either positive definite or positive semi-definite. Now, is cap sigma a valid covariance matrix? Yes, it is. Because cap sigma is square and symmetric and non-negative, it is a valid covariance matrix. All right, next, could cap sigma be the covariance matrix of a multivariate normal distribution? The answer is yes. Because cap sigma is a valid covariance matrix, it could be the covariance matrix of a multivariate normal distribution. And so with that in mind, we define a 2 by 1 random vector bold X with constituent random variables x1 and x2. The variance of x1 would be 4. The variance of x2 would be 4. And the correlation of x1 and x2, which you'll recall, is the covariance of x1 and x2 divided by the square root of the product of the variances, would be 1 over the square root of 4 times 4, which is 1/4 or 0.25. Now, does a PDF exist for this distribution? Yes. Because cap sigma is positive definite, its inverse exists, and so the PDF of this distribution exists as well. All right, I also want to look at how we might be able to check whether cap sigma is non-negative using the definition. And so let's let bold X be the 2x1 vector with constituent variables x1 and x2. And note that the inner product, x prime times cap sigma times x, is equal to the expression 4 times x1 squared plus 2 times x1 times x2 plus 4 times x2 squared. Now recall that by definition, cap sigma is non-negative if and only if it is either positive definite or positive semi-definite. It is positive definite if and only if the quadratic form x prime times cap sigma times x, which is equal to, in this case, 4 times x1 squared plus 2 times x1 times x2 plus 4 times x2 squared, is strictly greater than 0 for all non-zero vectors in two-dimensional Euclidean space. And it is positive semi-definite if and only if that same quadratic form is non-negative, greater than or equal to 0, for all non-zero vectors in two-dimensional Euclidean space, and if that quadratic form is exactly equal to 0 for at least one such x vector. So to show that cap sigma is either positive definite or positive semi-definite using the definition, one has to show that the conditions in the definitions hold for all non-zero x vectors in two-dimensional Euclidean space. Since the number of such x vectors is uncountably infinite, it is not possible to do this via enumeration, that is, by going through all possible x vectors and showing that the conditions hold. Instead, it would need to be shown mathematically, analytically. Now, on the other hand, to show that cap sigma is not non-negative, all that's required is that we produce one non-zero x vector in two-dimensional Euclidean space for which that quadratic form is negative, strictly less than 0. If we can find such an x vector, it would then follow by counterexample that cap sigma is neither positive definite nor positive semi-definite, and therefore not non-negative. The other approach to determining whether cap sigma is non-negative is to use the results based on characteristic roots that we have been looking at, which are in general much easier to check, at least when the characteristic roots can be readily obtained. In this example, given that the characteristic roots of cap sigma are both positive, we know that cap sigma is indeed positive definite. This implies that the quadratic form 4 times x1 squared plus 2 times x1 times x2 plus 4 times x2 squared is strictly greater than 0 for all non-zero vectors in two-dimensional Euclidean space. What I want you to do is to spend some time to see if you can find a way to show analytically, mathematically, that this inequality does hold for all such x vectors. The point of the last part of the example is to make clear what is required when using the definitions to show that a matrix cap sigma is non-negative, and what is required to show using the definitions that a matrix is not non-negative. Now, to show that a matrix cap sigma is non-negative using the definitions, the stated conditions must be shown to hold for all non-zero x vectors in two-dimensional Euclidean space. When using the definitions to show that a matrix cap sigma is not non-negative, all that's needed is to find one non-zero x vector in two-dimensional Euclidean space for which the stated conditions do not hold. So this is the end of this example. We will look at another example in the next lecture video.